Action!
We're good? Okay. All right, so talk is about monad transformers. I kind of anticipated what our audience would look like. A lot of you haven't had a chance to learn too much Haskell yet. That's fine. That helps me, actually, because I've spent a lot more time teaching the basics than I have the more intermediate or advanced bits of Haskell. So you're really just playing to my strengths. So this means that I'm actually going to spend a lot of this talk not talking about monad transformers or even monads. That'll come in the second half. I'm going to spend some time talking about functors and type classes so that we understand the basics before we move on to a more complex or stronger algebra. And that's going to be part of what you're going to learn. These are just algebra. So first off, functors. One thing to understand about a functor is its relationship to applicative and monad. I know you don't know what those are yet. That's fine. But anytime you have a monad, there's a functor in there somewhere. Monad is itself. You have a functor, and actually an applicative functor, before you have a monad. And we have to understand the weaker algebra before we can understand the stronger algebra. Okay, functor. So we implement functor in Haskell type classes. You don't have to, but it's the most convenient way to do so. You define a type class definition with the syntax in Haskell. Class, that's how you define the class for just defining it. You're just defining the interface. If any of you have done like Java, it's kind of like that, but don't stretch the analogy too far. And then functor is the name of the type class. And then we have f, which is it's a type. In this case, the higher kind of type, and we'll learn what that is in a moment. And technically, functor has two methods. We're only going to concern ourselves with the v method, which is fmap. And its type is a to b. So this is a function argument right here. So we've got a function within a function here. And that function is being passed as an argument. And it goes from a to b to fa to ft. And then we also have a couple of laws. One is identity. If we fmap ID, it should be the same as if we passed our value to ID. Identity in Haskell is just a function that takes the value that was passed and kicks it back out. So ID1 returns 1. ID, the string blah, returns blah.
I was putting my 1. That was 1. It returns 1.
Right. So the other is just, can we compose fmap? Can we compose two functions, f and g, fmap those composed functions and get the same result if we composed the individual fmap functions? And we should. And if it doesn't do that, it's a broken functor. Also, the identity law here, this is whenever you hear somebody, especially somebody with a more category theoretic mindset, if they talk about the structure preservation that functors guarantee, that's it right there. We shouldn't have messed with any of the outer structure that we're fmapping over by fmapping ID. That's why it's the same as ID. And I already went into some of this. I already talked about this being identity and about structure preservation. Without this, we can't compose things. We can't tease our code apart. Because this is about combining two functions and fmapping them all at once. This is about fmapping them independently. You're going to see what that looks like. In fact, I'll show you a quick example so that we can prove to ourselves that these things are true. So I have a REPL here. There's my fmap. The little, if you've used Ruby, you think that's a hash rocket. It's a type class constraint. It means that f has to implement functor. If you try to pass it a value that doesn't implement functor, it'll tell you done goofed. So fmap ID, who knows a functor? Give me a functor.
List.
Yep, list. Okay. What's going to happen if I pass that same list to just identity? Same result, right? Okay, that's identity. All right, what does it mean to have compositionality? We have +1 and times 2. And if I compose +1 and times 2 over 1, 2, 3, we get 4, 6, 8. But if I tease those apart, and instead I f-map them separately, we get the same result. That's the second law. I need to be able to do this with my functions, or I've lost all ability to compose and abstract my code. Absolutely mandatory. Otherwise, you don't have a functor. You have something that's functory-ish. Don't give it a functor type class if it doesn't satisfy the laws, because then you're lying to other people that ask for a functor. Okay. And I actually preempted myself here. I forgot what's in my own talk. All right, so yeah, identity, composing. Okay, so what is fmap? Can I get anybody to suggest what they think f-functors are about? What they are? Essence? I'm not expecting a category theoretic answer.
Applying a function to data inside a container?
That's reasonable. Yeah, that's reasonable. So I usually shy away from the containery explanation. It's a good place to start, though. Now, the reason I shy away from the container explanation is that you'll think it's about, like, okay, what do we think containers are usually in programming languages? Lists, trees, things like that, right? Are functors useful for those? Absolutely. But that's not what a functor is. That's a subset. So the reason the container analogy isn't a bad idea, especially to start, is that you're talking about an A type argument to some F. So this F, in some sense, contains A. But it doesn't have to. And that's why you have to be careful with that intuition. But it's definitely a good place to start. And what we're doing is we're applying this function to the contents of our F and getting FB. Does that make sense to everybody? You apply a function that goes from A to B to the A inside the F, and then we end up with FB. Just textual substitution here. Just pretend you're playing games with text. Makes it much simpler. That's what people talk about when talking about like type Tetris or playing with the types. You're just playing with text. Okay, so this arrow here, it indicates a function. This is actually the type constructor for the function. So f is itself a type constructor that's taking a type argument A. But actually, so is our little arrow guy here. So what this is indicating is a function that takes two arguments and returns one result. But the thing is that technically in Haskell, everything takes one argument. We're just nesting the lambdas to be able to accept multiple arguments. So the way this arrow works is it's right associative. So the parentheses associate from the right, which means that we can parenthesize it like this. So there's two different ways you can think about this. You can think about it in terms of application, which is what was hinted at with the container analogy. And what we mean by that is we're applying our A to B inside the F over the A and getting the FB. The other way to think about it is you're lifting it over structure. And that's what this parenthesization is intended to highlight. We're transforming our function. We're transforming our function A to B into a function that takes an FA and returns an FB. See the symmetry? Now, you can, a couple different ways you put that is you're lifting A to B into the environment F, and that environment F is polymorphic because it's the functor type class, and it can be any functor you want. Another way to think about it is that you're mapping A to B over F. Don't get too hung up on the words, though. What defines functor is the types and the laws. That's it. Any English word explanation, if it disagrees with the types of the laws, then the English word explanation is the thing that's wrong, not the types of the laws. Okay, so here's the list functor. All we did was we took our F, our FA and our FB, and we changed it to list of A, list of B. List type constructor has a little bit of special syntax to make it look kind of like a list or an array. That's why you have the brackets around the A and the B there. How do we implement the list functor? We're using this implementation on purpose. You will find out later why. But this is actually just map, right? It's just polymorphic map. Okay, the way we implement map here is with fold R. We're folding a list, and all we're doing is applying the function to the contents of the list, And we're composing that with consing the result of having applied that function to the contents list, and we're folding it into a new result list. What that is like is it's as if you had this list, fold R, cons, and then we're going to do +1. Okay. That didn't break? Awesome. All right, so what's happening? This gets applied to 1, and that returns 2. And then that gets const. That's the const constructor to const something onto the head of a list. If you want to know what that looks like, it's like that. Okay, so then we're consing the result onto the list. You could think of it like this. If you wanted, that's not strictly accurate.
Can you move it up?
Sure. Okay, so, but because it's in terms of cons, not the list syntax sugar, you're consing the results with the functions applied to them. So it would be more like, and so on and so forth. All right. And when we get an empty list, we return an empty list. Fold R is handling that for us. If we just defined fmap to map, it would handle that as well. You have to handle the empty list case. All right, another thing to notice here. In this fmap, we're going to talk about a list of A. That's going to be the type when we specialize the f to list. But in the type class definition, instance is how we define an instance of a type class for a particular type. The way type classes work are that you're supposed to have unique instances, a unique pairing of type class and type. So you shouldn't have multiple list functors. There should be one canonical list functor. There's several reasons for that. I won't go into them right now. But there's no A in there, is there? Can anybody tell me why? Why there's no A in here?
Because it's the type constructor that we want.
Right, exactly. If we look at our type here, our f has to be able to be applied to an argument A. That argument A being what we're mapping over. We don't have anything to map over if this is already fully applied. Because this is actually like a function at the type level that takes an argument, which is itself a type. It's a higher kinded type. When we want to talk about the structure of types, we talk about kinds. And we will go into that. Here's maybe. Same idea. We took f, we replaced it with the type constructor for maybe. Maybe is why we don't have null errors in Haskell, because we just replaced it with a simple sum type. Well, not too simple. It's still higher kinded. But the reason we want a higher kinded maybe type is so we don't have to re-implement it for int and string and all the other types in the universe. We parameterized it over A. So maybe can contain any A. Well, any type of, kind star. You can't contain a value type with the magic hash. But most of you aren't going to use that, so don't worry about it. Steven does, but most don't.
What?
Hmm?
A what type?
So you're gonna see like the kind syntax in a few slides with it. So kind star is the default kind for concrete types in Haskell. That an example of kind star would be like int or string. String is actually just a list of car, but it's still kind star because you took the list and applied it to the type argument car. Int is just a built-in type that represents a hardware integer. It's not a higher kind of type. Int is just a concrete type. It's also a pointer. It's a pointer to int. The default types are reference types that have pointers. So star is just a default reference type. The alternative is a value type. So you can have, as if in C you didn't have a pointer to an int, you just had an int. It's that idea. but there's kind of a line drawn in the sand between where you can have value types and reference types. You can't do certain higher level things. Also, reference types, they're actually the kind star. They're all pointers to value or func, actually. They're not necessarily a pointer to value, because otherwise it's not a lazy language, right? Whereas value types, no func. It's just the value. Okay, so maybe. That's why we don't have null type errors. We don't have to implement maybe over and over for every concrete type in the universe. Why? Because it's higher kinded, like list. The definition of maybe, we didn't include here, is this. This is how you define it. You could define your own if you wanted. It's not built in the compiler. It's not some one-off magic. You can write your own. That's the definition. So the first thing to notice, all right, this equals sign. Left-hand side, type constructor. Right-hand side, data constructor. This is what you use in your code. This is what you use in your type signatures. Type signature, code. Code, type signature. Now, it takes a type argument, A, right? Also, this A is not the same A here. They aren't syntactically significant outside of the expression they're used in. The letters have no meaning outside of the one, scope. Okay, we have a nullary constructor, nothing. It's just a value that stands for itself. It doesn't take any arguments, it doesn't do anything, it just equals itself. That's all it's there for. It's just there so you can pattern match on it. But then we also have this pipe here. What do we use pipes to represent in programming languages often? Or. Well, that's how we represent some types in Haskell. So it's kind of like in extended Backus NOR grammar. Have you ever seen that? It's kind of like disjunction. It's the same idea. It's a sum type. It's saying when you have a maybe A, whatever that A might be, you have nothing or just A. Now, just is not a nullary constructor. It does contain something. It's a unary constructor. It contains one argument, one thing, and that's just A. So what you have to do whenever you have a maybe is you have to handle the fact, not manually, there's higher order functions, but you have to handle the fact and confront the fact that you may not have a value. So anywhere in Haskell code where we might have otherwise returned null, which doesn't exist for us, we'll actually just return maybe. So now you know in your types exactly where you might not get a result. You can just grep for maybe, and you'll see all your type signatures where you may not get a result. In practice, in more serious applications in Haskell, you won't use maybe that much. You'll end up using either for validation, something like that. Not terribly different though, same concept. Okay, so what type is that? Maybe, well, it's technically polymorphic, but yeah, no, it's okay. It's a morally correct answer. Well, the monomorphism restriction got turned off, so the literals are all polymorphic now. It can be any num you want. But I'm going to pretend they're int or integer. Unless I put like a dot and then, it starts looking kind of floaty. But anyway, yeah, it's maybe int. By declaring a just constructor with the type of value int, it can just infer the fact that it's maybe int. I don't have to tell it. The values are witness to their types, and that's how the type system knows what I'm talking about. And what type is that? Anybody tell me what type that is?
Maybe A.
Right. And it's A because we don't know what our A is. We haven't given enough information to. So in Haskell, one of the nice things is that not only do we have polymorphism, but we have polymorphism by default. The inference algorithm will find the most polymorphic type that is correct. And the most polymorphic type that is correct for the nothing value is just maybe A, a rigidly polymorphic A. A could be anything in the universe, we do not know. In fact, as a silly example, I can actually assert an impossible type in here because there's no witness to the contrary in the value. Whoops. It doesn't want to show it, but yeah. Here, we're doing the getting down to the bottom thing again. Let me actually, yeah, there we go. So yeah, it let that fly even though A to B doesn't exist. It actually does, I know, but don't use it. It technically exists, but technically, like in the type system, there's no such thing as an A to B. Can anybody tell me why A to B doesn't exist? In principle?
Because where do you get B from?
Yeah, exactly. You don't know anything about A. There's no information there. It doesn't tell you anything. So you have no way to get from A to B. How would you? Incidentally, the function that you're not supposed to use that is A to B is unsafe coerce. It doesn't do anything. You're just casting the type. But that's why it's called unsafe coerce.
How's that any different from to string?
It's a different thing. To string's a coercion to string. That would be like show.
It's like
Yeah, you could have an A to string that just returned a constant string for all types.
yeah, 'cause
Well, there's
you know
show.
what the,
How many
you know
times
what
is-
the what's going that it's a string you're entering, whereas B.
If I have a
Yeah,
function that
totally.
ignores its argument and just returns a string over and over, I technically have polymorphic T to string, right? It's a trivial sort of function. It's technically correct, though. Why can it be polymorphic? Because I'm not doing anything with my argument. If I'm not doing it with my argument, it can be strictly any type in the universe. It doesn't matter. That's also why ID works for everything in the universe. Because it's not doing anything with its value. It can be any type. Because we're not expecting anything. We're not expecting any structure or type classes or anything. Okay, so, and just so you don't get the wrong impression, stuff with unsafe in the name actually don't get used in practice in Haskell code. You don't have to worry about it. All right, so the implementation of functor for maybe. We're f mapping f over maybe. F is our function. If we have just, we're pattern matching here, which is a way of dispatching on cases at the top level of the function. We just apply our f to the accent side, and then we rewrap it in just. Why do I rewrap it in just? What happens if I get rid of the just constructor? Is it going to type check?
No.
Why isn't it going to type check?
You're not returning you're not returning maybe value for that.
Right,
Or you're not
right.
returning a value that's still within the
Exactly. It has to stay maybe B. I can't implicitly like maybe return maybe and then not return maybe. Doesn't work. Because I might not have anything. I can't guarantee I'm going to have a result. Maybe forces us to confront that possibility and not just, sweep it under the bed. Okay, so if I f-map increment over just 1, I get just 2. If I f-map increment over nothing, I get nothing. What does this save me? I don't have to case match every time I want to apply a function to something that's maybe, or list, or either, or validation, or const. There's a really long list of things that are functors, and I don't have to care about the specific details of those types in order to manipulate them. Functor lets me do that. So, kinds. Preempted myself again. Int, float, char, they're all kind star. They're just concrete types. But lists, little, brackets, they're kind star to star. They're a higher kind of type. They need an argument before they become a real type. Concrete types have values at runtime. These do not. Anything that isn't concrete, it doesn't exist at runtime. It only exists at compile time. This is important because that's how you know when you look at the definition of functor, when f gets applied to a, you can't be talking about an fa at runtime unless it was star. And what that tells you is it actually tells you how the kind inference in Haskell works. If there's only one argument left to apply to make it a concrete type, in the case of f applied to a single argument a, then we know that it's just star to star. It doesn't have to be. If it took 2 arguments, it would be star to star to star. So I shouldn't say all. We mostly use kinds. They're like, again, types about types in some sense. Types 1 level up. We use them mostly to talk about the structure of type constructors, which is really just a way of saying how many arguments do they take before they become a concrete type. That's not the only use for them. There's also constraint kinds and other things. I will not teach you those here because they don't matter for our purposes. But if you want to learn about them, play ball. Okay, so Haskell has kind inference, unlike certain languages. You don't have to specify them. It can just figure it out from the definition of the type. You can query the kind in the REPL using the :k or :kind. Colon's how GHCI knows you're trying to talk to it and not write code. It's just a command, just like the colon T thing I was doing with the types. All right, so first, trivial data type. Here's our type constructor. Remember, left-hand side, types, right-hand side, values. All right, kind, trivial 0, star. Why is it concrete already? Because there's no arguments, and it just has a null-array constructor. So it's already concrete. It's a trivial, type. It doesn't do anything. Well, it doesn't stand in for itself, but that's it. It's concrete already. All right, trivial 1, A. How many arguments does it take? One. All right, so it has to take one argument before it becomes concrete. A single star.
But I think it's important to say that it's taking the argument on the type side, but not on the value side, right?
Right. Well, yeah. So you can have witnesses to like inhabitants of that type that don't take any extra arguments, like nothing and maybe. So it is strictly speaking at the type level. That's actually one thing these constructors highlight, is that it's not a real type until we apply A and B, but we never actually use A and B. Where's A and B in here? They're phantom. They're what's called phantom types. We actually have a use for phantom types in Haskell. We use them for like a primitive form of type indexing. There's more advanced ways to do that, such as with generalized algebraic data types and type families. Also, I'm not going to go into that today. Sorry.
So just so I'm clear, you can do that in the same REPL session. In other words, you can have trivial be.
This is me copy and pasting from GHCI. The REPL is not like some stripped down version of GHC. As far as I know, there's like, Steven, is there anything the REPL can't do that you can do with the compiler that isn't strictly related to compilation? Because I know it's an interpreter, right? But like, I don't think there's anything.
So if you just type in trivial.
Sorry, hold on. I'd like to, Steven. What? No? Okay. Yeah?
So if you just type in trivial, if you just type in :T trivial, what are you going to get?
Colon T trivial?
Yeah.
It'll say trivial 2, AB. You remember how nothing was maybe A? Our AB will be polymorphic here as well.
I think he's just asking, you're reusing the word trivial.
Right, yes, that's
construct-
exactly what I'm saying.
I see. I'm sorry. Yeah, it just gets shadowed. We don't have overloaded record fields yet. We will in the next version of the compiler. And it will basically turn the constructors that overlap in name into basically an interface, a type class. And they'll become polymorphic. Whether or not you think that's a good idea,
I'm about to test
you missed it. Mailing list debate already happened. It's coming. It's kind of bringing us halfway to row polymorphism. I have no opinions on it. I mean, it's a pragma, right? So if I don't want it, I don't turn it on. If I want conflicting record accessor names to throw a warning or error, then I just don't turn on the pragma. And if other people want to use it, that's their problem. I'm going to play with it, and I'll make a decision then. But yeah, so in the REPL, yeah, you're just shadowing. It's just introducing a scope and shadowing what was previously
Connect
there.
the dots for me. Why did we start talking about records when we were talking about constructors here?
Well, because so this is just like a null-array constructor.
Sure.
But whenever anybody talks about like overlapping constructors, they're often talking about record accessors more than they are actual constructors.
Okay.
So it just, yeah.
Same discussion.
Yeah,
Okay.
it's just kind of the same topic,
Okay.
like overlapping, yeah. Because usually it's record accessors that overlap, not
Sure.
normal like null-array constructors. Because you'll have like, name, right? How many records are going to have name? I actually prefer to just prefix them and say like what it is, but some people really like brevity. I don't know. If you've looked at Bloodhound, you know I don't care that much about brevity. Okay, so kinds of day-to-day types we actually use, not trivial, which just, we're just slapping phantom type arguments onto it that we never actually use. Not that it would be that interesting if we did, but anyway. All right, so the bracket syntax for list, this is how it's defined in base, if I remember right. But it's special syntax. If you're going to re-implement list yourself, which you can do, again, not special, written in the language. Haskell is bootstrapped the same way lists and schemes are. No magic. All right, so you can just write it like this. just give it names. You could use a, you know, an infix cons if you wanted, but I didn't here. Okay, so list takes one argument A. What is list? It's nil or a cons cell. What is it a sum of? It's a sum of a null constructor and a product. Cons is a product. It's, you can think of it as a record. It's not really properly a record because we're not defining it so. It's just a product. We're not giving names to the individual fields. And what does a cons cell contain? A value and what? Rest of the list. Head, tail, car, cat. This is equivalent to a linked list. Pointer to value, pointer to rest of list, until you reach the end of the list. Okay, that is kind star to star, because you need to apply one argument, A, before it becomes specific type. Maybe A, nothing, or just A. I already showed you that. Same deal, one argument, star to star. Either A, B, two arguments. Why are there two arguments? Because left and right can be different types. Are they required to be different types? You know the trap. They are not required to be different. They are simply allowed to be different. You could have an either string if you wanted. Don't do that. But you could. It would be silly, but you could. Also, incidentally, the two tuple is in some sense an anonymous product. Either is kind of the anonymous sum, because you can encode every sum in the universe just by having two sides to the sum. You can encode every product in the universe just by having two sides to the tuple. That can be homework if you want to prove that to yourself. But you can just nest them. That's why. You can just nest. Okay, so the kind of either is star to star to star, because it takes two arguments. First type argument, second type argument, then we're concrete. Functor and its kind. Functor is kind star to star, or rather our F that functor talks about needs to be kind star to star, because it gets applied to one argument. It can't be any other kind, because A, it needs to have an argument to be applied to begin with, and it can't have any extra arguments remaining to be applied, because we can't talk about something that isn't star at runtime in our actual code that executes. And that's how the kind inference is able to figure out, hey, F is star to star. I don't have to say so. I just figure it out. For functor, that's kind of trivial. When you start writing something cleverer than that, kind inference becomes kind of nice. I think mu would be a good way to demonstrate that. It's not immediately obvious what the kinds of things in mu are. I'm not going to cover mu either, sorry. Stephen knows what I'm talking about, though. Okay, so, all right. I defined fmap to undefined, aka the almighty bottom, which apparently terrifies some people. I actually really like it, because I use it for sketching out code I don't actually want to write yet. Basically, bottom will pass as any type in the universe, and it'll just say it's correct. The type system just go, yep, all right, looks good. No type checking. Why? Because I don't actually care what the implementation of either is right now. Why? Because I'm actually going to ask you about kinds right now. I'm going to talk about higher level stuff. Then we'll talk about the implementation. All right, is this going to work? I'm going to outsource my type checking. We're not going to ask the computer, we're going to ask humans. Is this going to work?
No.
Okay, anybody want to tell me why?
The kind's not right.
That's right, there's a kind mismatch. There's our kind mismatch. They wanted star to star, but either is star to star to star. Okay, but if you've written any Haskell, you know there is a functor for either. So how can this be true? How can we have a functor for either if there's a kind mismatch? What did I say these were? These are type constructors. They're like functions at the type level. What is the one thing you can, well, for my purposes, what is the one thing you can do with a function?
Partially apply.
Yeah, you can partially apply. Just apply an argument. The distinction between apply and partially apply in Haskell is kind of, it's all kind of the same thing. But yeah, you just apply an argument. Because if you apply an argument, what are you going to get? You're going to get star star, right?
Actually, I'll ask the question because how do you apply to the second argument instead of the first one?
You're getting ahead.
Oh, you're going to cover this in your slides?
Oh, yes.
Okay, good. Yeah.
Oh, yes. This is like a pivotal point, yes.
I know a little bit of Haskell, but I haven't looked that up yet.
Okay. So, we already covered this. We're going to apply it.
Flip.
Also, the order of type variables will become important when after you already understand functor, and then you go to understand contravariant, and you're going to say to yourself, what the hell is going on? And knowing this is going to help you out a lot. Okay, so we can't talk about a functor for either. But if we have either A, B, we can't talk about a functor for either A. So we've partially applied, whatever, who cares? We've applied the A, right? Okay. How many, if I've applied A, how many arguments do we have left before we have a real type, a concrete?
Just one.
Just one, right? So that gives us a star to star. Now it's going to type check. Actually, it won't because it'll complain about your either conflicting with the existing one in prelude, but if you turn on no implicit prelude, then it'll type check. But that's irrelevant. That's not germane. Okay, so ordinarily, either maps over, as in this is when we actually apply our function f. Normally, f map maps over the right, not the left. We're going to find out why. All right. So I don't want it to. Let's say I'm a left-handed person. I'm not actually, but let's say I am. And in my protest of prejudice against left-handed people, I'm going to make a functor for either that maps over the left side. Why can't the left be the default, right? Why do we have to presume it's always the right? Okay, so my instance of functors for either A, because I can't talk about a functor for either. That doesn't even real. Doesn't exist. Not a thing. But there is a functor for either A. Right? Okay. And then I'm just going to implement it. In the right case, I ignore the function, and I kick the same value back out. Basically, identity. And in the case where I have left, I'm going to take my f, and it's going to look a lot like maybe here. I just apply the f to the contents of the data type, and then I reconstruct the left value because it has to stay in either. Okay, is that going to work? We'll even take let's take a vote. All right, raise your hand if you think that's going to work. Oh man,
Wait, what?
y'all are on the game
I
here.
think it's gonna work.
You think it's going to work?
Well, I haven't looked at it too much.
Okay.
True.
All right.
Looks good.
Raise your hand if you think it's not going to work. Okay, people that know me better. Yeah, it's not going to work. All right. What does a type error mean? What does it mean? Doesn't match expected type A with the actual type B. All right, why did you expect type A? Because we were mapping over left A. But the actual type wasn't A. It was B. Can anybody tell me why the actual type was B?
That's what the constructing of the type of the concrete type put in, or
Because these names are from different scopes, right? We have to go back. Here's slide.
So you're both like converging. I'm just gonna, I had a slide ready for this. Okay, so I was prepared. All right, so my f, we talk about an FA. If I'm talking about an A inside of f that we're mapping our function over, and we have either A, B, remember the A in here and the B in here is not the same as that in the definition of either. These type variables are independent of each other. So that's the first thing to realize. I could have made that more obvious with different type variables, but you're gonna just have to get used to the fact that everybody uses A and B all over the place. Like you're gonna see A, B, S, T, F, M, W. You're gonna see a lot of those. Who can tell me what W is? What do we use W for?
Right? Something?
No,
I don't know.
coming at.
Okay.
Yeah.
This makes sense.
Because it's a
Sure.
dual monad, so
Sure.
it's
Yeah.
upside down and down. Yeah, I know.
It's like Mario and Wario.
Yeah, it is actually. Yeah. So, okay. So, You had the right idea, and you had the right idea. So let's merge them together. All right? When we applied A in either A, B, the A is out of scope. It cannot be addressed by the type class. What is left after we apply A? What's left? Either A, B, left A, right B. What's left if I apply A out of scope? The B and the right. Right? It's making the same words
I
here.
think it would be instructive to write out the signature of F map when F gets specialized to either A.
Yeah. It's
Just like literally writing it out. So it would be like F map of type takes a function A to B, arrow,
Yeah, I know
and
what you
then
mean.
replace the F with the either A, and you might have the name
okay.
of
So we
prime,
have
just the-
A to B. So one thing that's going to make this a little awkward is the type variables. So I'm going to change this to C to D.
You can do A and A prime. I think that would work.
And well, so if I use A here, they could mistake it for the A that we applied out, right?
Well, if you're just whatever.
Let's
whatever
do
you
B
want.
to B prime. Yeah, B to B prime. Okay. And then we go to, all right, what's our F? Our F is what? Either A, right? That's our F, but we need to talk about FA. So in that case, we actually mean B. And then we end up with either A, B prime. So we're not allowed to touch or talk about the A in either A, B because it's not in scope here. It's hidden in the F. It's not being addressed by the type class. We can't talk about it. Not a thing. Just not there. So our F is either A, not either. And our A in FA is actually the B in either A, B because the A got applied out. So how do we make this work? This type checks. My left biased either, it works now.
Oh,
Now's your time to shine. What did I change? Suka?
I'm so missed something. What did you?
The left works now.
Oh, I see what you did. You flipped it.
Flip to B and
Luxway.
A.
Got it.
Yeah, I just flipped B and A. That's all. Boom. Left biased either. Now lefties can conquer the world. Right? Begins here. All right, so we'll tell the government. All right, so now it works. And just real quick, this worked because now we're applying the B out of scope, and now we can talk about
This
the
is a
A.
little bit of a different solution than what I was really asking. Because, like, let's say that you have a data type that's already. Oh, are you going into that? Okay, sorry.
We're not. We haven't even gotten to monads.
Table. I'll table it.
Yeah, we haven't even gotten to monads.
Drink
yet.
beers.
This is ostensibly about monad transformers, and we have addressed neither of those words. Okay, so let's talk about functions and their type constructor and kinds. A to B is an infix type constructor. It's in between the two type variables. It's the same kind as either because it takes the same number of arguments. Letters still don't matter. By convention, A to B. All right, it's kind star to star to star. There is no functor for function by itself. But what can we do with it to make it star to star? We can partially apply the type. And that's what we do. We take the function type constructor, and we have to parentialize it like this because it's infix. Basically, we're making it like a prefix constructor when we do that. It's just syntax. And then we partially apply it. The first argument in the function type is the argument type, actually. So when we partially apply the function type constructor, we're making that go away. We're taking that out of scope for the functor. So the functor must necessarily be mapping over what? If we're talking about functions, and we took the argument out of scope, what are we transforming with the functor? What's the other thing?
Result.
Right. We're transforming the result. The implementation of functor for this type is just composition. It's just composition. That's it. what does the type for that look like? Well, it's actually a little bit hairy for new people. So bear with me here. Okay, so what's going to kill you here is that this is just a more polymorphic, more general version of that. That was crazy, right? Like, how could that be the case? That doesn't even make sense. Okay, let's find out why. And that is how it's implemented. I'm not, creating a fantasy land here. All right, so let's talk about how that can be the case. Well, the first problem we have is that it seems like this takes, a different number of arguments, right? But it doesn't. What did I say? Every function in Haskell takes one argument, returns one result. Everything. It's just a question of whether the result is more lambda stuff. More lambda stuff, more arguments. Okay, so because of the way the associativity for the type constructor for function works, we can parenthesize it like that. Now we have the same number of arguments to our human eyes, right? Okay. All right. So how do we jigger this around? Here's what's happening. What did I say got applied out of scope? What's in our F for function? We're partially applying the argument type, right? So we're not touching that, right? Now, I know this is alien for a lot of you, but just look at the text. Don't get too heady about it. Just look at the text. A gets left alone, right? See, we don't touch A. We don't change the argument type. We just change the result type. We're threading the application of this function into giving its result directly to that function, and that changes our result from B to C. So composition is actually post-composition, because we're composing the functions applied through the results. If you want pre-composition, you want a contravariant functor. And that gets into what Susan wants to talk about, which you're not going to do. Sorry. You want the type constructor op, by the way, OP. If you just look at contravariant, Edwards library, you'll see OP in there.
Okay, that's good to know.
And what it does is it just flips the arguments around for the function type. That's all it does.
Okay.
And then pre-composition for op is just you're transforming the arguments.
It's bad at table with topics.
Huh?
I'm just joking. I was completely fine. Keep on going.
All right. So does that make sense? That this is our f, that is our f. There's our function that we're mapping, and that, B to C to C. And how is it implemented? Well, we have another way we can implement it. So we can use the dot, but we can be a little more explicit here. We could say,
Do you ever find yourself rewriting the type variables just to see it a little more clearly, like do the crypto quotes game?
yeah, all the time. We could do
Yeah, I was going to suggest, in the fmap signature there, you could rename mentally A to B.
Yeah.
So
Yeah.
rename A as B, rename B as C, and then it lines up a little better with the compose.
Mm-hmm.
That's all.
So, okay, so it's that. Okay, so that's where the extra argument came from that we weren't really talking about in the functor, kind of, is we're returning a lambda that takes an argument. So that argument is x, we don't know what x is, we don't care what x is. All we care about is that we're applying our g to x, and then we're applying the result of that to f. Just like piping, like Unix pipes. That's all it is. We're just threading results through transformations. All right, and that syntactic form of fmap for functions, That's going to be important later. Going to be really important. Okay, so weaker and stronger algebras. For our purposes, I'm just going to say that algebras are a set of operations. What is that set of operations? The operations are the methods in the type class. The type class itself is the set. It's ad hoc polymorphism. It's parameterized by what type you're talking about for that type class. And the most apparent way to demonstrate that would be something like, okay, so monoid is a type class. Mempty is just it's polymorphic, but it's a concrete value.
Never said it out loud. That's so fun.
Oh yeah, I say it all the time.
How do you pronounce that?
Mempty.
Speaking of pronouncing, how do you pronounce the equals arrows thing?
Equals arrows thing?
Like the thing between...
Constraint.
So monoid A, constraint A?
No, just requires monoid. Monoid constraint. That's so the hash.
Call it implies.
It's just I just say it requires monoid A, or A has to be a monoid. Another way you can think about it is it's actually like an extra function argument, because it's almost as if you're threading the type class implementation as a set of functions that you're carrying around and then applying, but it doesn't matter. That's another talk. All right, so what's mempty? Well, it depends. Whoops. Oh, it wants a monoid for the A inside of maybe. Anyway, point is, I'm too lazy to write the constraint. Okay, so mempty list of A, empty list. So we're dispatching our mempty on the fact that it's a list. The A doesn't matter because the mempty doesn't have a witness to A, so it doesn't matter. And in fact, monoid isn't actually about higher kind types, so it's monomorphic in that respect. Okay, so weaker and stronger algebras. All right, so I said every monad also implements applicative and functor. That means it's stronger, contains more operations. It's a superset. That makes it a stronger algebra. The set of operations is larger. All right, so what's the advantage and disadvantage? Well, with a weaker algebra, you can decompose what you need more, and more types can implement a weaker algebra. But you can do more with a stronger algebra. Often what you'll do in some cases, especially if you're commit, you'll start with a stronger, more unified algebra, and then you start teasing stuff out and abstracting them into independent concepts. And then you end up with a type signature that's not long, but it works. Okay, so monad. It's not a semicolon. Not a semicolon. Nothing to do with semicolons at all. Nothing to do with imperative programming at all. Yes.
Is it a burrito?
No. Yeah.
Why are you skipping applicative right now?
It doesn't matter. No. It's a good question. I considered it, but I realized it didn't matter.
Okay.
It's important if you want to actually write Haskell. It's not important for understanding monad transforms. If that makes any sense. I will mention applicatives later.
Okay.
Like when I talk about what compose does and doesn't work with, applicative will come up. But
It's just
applicatives are kind of brain bendy for people, and I can't spare the time. But it's good that you brought it up. You should all learn applicatives.
in the next.
I'm just not going to teach you right now. What?
Because in the next version of GHC, if you want to implement,
Yeah.
you want to implement a monad, you have to implement applicative
Yeah, the applicative monad
and
proposal.
functor.
Yeah, which would be nice. Previously, so historically, you only had to implement functor to have a monad. They're jiggering things around so that the full sequence of functor to applicative to monad is being recognized. So now, if you want a monad, you don't just implement functor, you implement functor and applicative. That's all. It's going to happen in the next version of GHC. It'll break some people's code, but progress, right? Progress is good. Yes? Okay. All right, so monads, not a semicolon, nothing to do with imperative programming. It is just that. It's that type class. All right, so I did change things a little bit from the way monad is defined in Haskell. Doesn't change the semantics, just the syntax. One is I called it bind. People still call it bind, but it's that. The caret equals. I didn't use that because it doesn't matter. Remembering the syntax is not the hard part. The hard part is thinking in terms of abstract algebras. That's what's alien. That's what you need help with. Okay, so the other reason I changed it is I flipped the arguments. Yeah, I know there's a flipped bind. I don't care. It still has like nonsense syntax. All right, so.
What was your reason for not including return?
I'm sorry?
What was your reason for not including return?
Doesn't matter for now.
Oh, okay.
Yeah. With monad transformers, the applicative part just doesn't like. Well, it will. I'll use return later, but it just like doesn't matter.
Oh no, that's cool.
Yeah.
It's just okay. Never mind. I think I understand what you're saying.
Yeah.
That's fine.
No, that's fine. It's fine. So yeah, so return in monad isn't actually unique to monad. It's actually pure from applicative, which then harkens back to what I just said about making monad be based on applicative instead of directly to functor. It's really simple. It's a little weird looking if you're not used to it, but you just go to A to MA. Well, what does that mean? All right.
Well, you can't state the ones.
Well, if I have a number, I'm going to monomorphize this so it doesn't look weird. Okay, so if I return 1, all right, but what if it's that? Whoops. Okay, and then, no. Yeah. So what it's returning or injecting the value into depends on the type class. And it should be able to use maybe again. Hopefully it won't sandbag on me. There we go. Okay.
So quick quiz. Think about, so does anyone know why return 1 when he just typed it without the type integer, just returned a 1?
He's working in IO right there.
yeah, and when you print an IO value, you don't see a type constructor for IO, or sorry, a data constructor for IO, because there isn't one. It's an abstract data type. IO is actually really simple. Anyway, okay, so if I say it's list event, we just inject it into a list. If I say it's maybe int, we just pass our value to just. It's just a way to go from A to MA. You need it for things. You'll see. Okay, so one thing I'd like to highlight here. So this side by side. All right, fmap, bind. We can tell the difference. What changed?
Well, there's an F in the end of your functions.
Right there?
Yes.
Well, end of the function or end of that function.
Excuse me, but there's an F.
Okay, so, and if any of you want to know what applicative is, just take this F and like move it like right there. That's it, that's applicative, you're done. Okay, so, what we did was, instead of A to B, we have an A to FB. What does that change? What does that change? All right, our A to B in functor, all it can do is just transform, return a new value based on the contents of whatever our FA is, right? But this gets to return more monadic structure. This actually gives us more power. We can do more things with this algebra. You will find out what those things are soon. Soon. All right, here's the thing though. Bind isn't strictly essential to monad, because bind is actually join composed with fmap. Because it looks a lot like fmap already, right? Looks really similar. I mean, it's mostly the same. Just have that F there. But if we just fmap instead of bind our A to FB over FA, what type would I get if I fmap that?
FFB. FFB.
Yep, we get FFB. We get an F inside of another F. But that's not what we want. We want an FB. One F. Well, fmap already exists in functor. right? So f mapping a monadic function isn't really specific to monads. What is? Join. Oh, I gotta import control monad first. There we go. All right, now we can squish it. However you want to think about it, doesn't matter. MMA to MA. And that's how we end up with FB instead of FFB. Ding, ding. Okay, let's monomorphize it so it looks a little less crazy. Look familiar? That is bind for the list monad. Concat for list is just join. Map for list is just fmap. So bind for list is actually just concat map. That's all it is.
Is that a flat map? It's column.
Yep.
Yes.
Same thing. Except with a much better name.
All right, so monomorphize a couple here. Bind for list A to list of B instead of A to B. List of A, list of B. And for maybe, A to maybe B, maybe A, maybe B. Now what does this let us do? What can we do with this that we couldn't do with the functor? We can choose whether or not we want to return the result. We didn't have a choice with the functor. We have to go from A to B. Now we can return a maybe B, but then we'll just be nested. So what this does is it gives us choice. We can say, don't return anything, fmap. But I just fmapped it. That's not really quite as useful. But if I bind it, I get nothing. So now I can manipulate the structure that gets returned as I'm mapping my functions as I go. It's the production of nested structure. Incidentally, when you have a co in front of something, you have a dual. Monads produce nested structure. Co-monads collapse enclosing structure. It's the opposite. We'll figure it out later. All right. So, the implementation for list monad. Remember how I said I didn't define fmap to map? Does anything look familiar here? Why didn't I define fmap to map for the list functor? What symmetry was I trying to show you?
Full.
Well, I only changed one thing, right? Instead of cons, I'm using concat. Well, concatenate, I should say. Concat's a different function. But I'm concatenating my results as I map the function over the list that I'm mapping over. And the reason I'm concatenating them is that my f is producing more lists. So I take an x, I return x, x plus 1, x times 2. All right, now I can fmap that over a list, but now I have nested lists. It's not really what I wanted, but what if I bind it instead? Now it's one list. So, I'm giving more power to my monadic function. It gets to produce more structure. What is that structure? Whatever your monad is. It's polymorphic. Just whatever your monad is. Doesn't matter what it is. This is pretty useful. Because imagine you have like a tree an AST for an interpreter. Now you could just transform that tree, but what if you could produce more evaluatable terms as you transform the tree and then reduce them as you do so? That actually ends up capturing a lot of business logic patterns. You'd be surprised. Okay, so the instance of monad for maybe is just this function maybe with a default to nothing and then FA. All right, so that is slightly cheating, but he has a reason for it. So, oh yeah, I should tell you, I forgot to say this at the introduction. This talk is heavily based on Tony Morris's talk on monad transformers. Only really the first half is original. The second half is me mostly repeating what he said and wrote, which is starting now. Okay, so maybe. All right, there's the maybe function. What does it do? B, A to B, A to A, B. Okay. So the reason we can use this to define our monad is that B doesn't have to be maybe, but our monadic function is producing some maybe structure. So then our default value for B, because what maybe is doing is it's a combinator for handling the nothing case, we just return nothing. To see what that looks like, you can just there you go. Bind for maybe.
So quick aside, actually, can you go back to the, are people familiar with this idea of having functions that sort of encapsulate pattern matching? So the lowercase maybe, it's kind of like doing a pattern match on maybe, so maybe has two cases, right? Nothing and just. So the first argument B is what you do in the nothing case, and the second argument is when you have a just A.
So to explain what he's talking about, you would normally have to, so there's two constructors of maybe, just and nothing. You would normally have to create like two branches for each case and then specify what you're doing for each of them. But that like shoves your code starting, like off towards the side, and then now your code is somewhere at the end of the line somewhere in Timbuktu. You're really mad, and that one Vim user who always complains about ED columns won't shut up. So if you don't want that to happen, you use higher order functions, combinators, things that abstract patterns.